Okay, I think we will make a start to the session and we can let people into the room as they arrive. So welcome everyone. My name is Sarah Buchanan. I'm the host for today and I work for the Construction Scotland Innovation Centre. We're delighted to be co-hosting the session today. The Energy Technology Partnership is hosting this webinar series as part of their annual Energy Innovation Emporium. And this seeks to inform the global energy community on how Scottish research and innovation can help deliver the huge, challenging carbon emissions reductions targets that we're all going to be working to for the next 5 to 10 years. The topic today is looking at how we harness technology to work within those carbon reduction targets within the built environment. So we know we need to change. Why not use technology to do that? Specifically today, we're going to be looking at the software and simulation for achieving low carbon buildings. So thank you to all our speakers for being with us today. I will introduce everyone and their topic as we go along. And of course, we need to do some housekeeping. So the event is going to be recorded today. You will be able to look at it afterwards. Please keep your mic and camera off. And of course, your opinion, your questions absolutely matter to us. If you have anything that you would like to ask during the session, please just add it in the chat box at the side and we'll get to it in the question and answer session. If we don't manage to get to your question today, we will come back to you after the session. So without further ado, I'd like to invite our first speaker, Dr. David Jenkins, the ETP Energy Efficiency in Buildings Theme Coordinator. He's from Heriot-Watt University and he's going to tell us a little bit about the theme that he works under. Thank you, David.
Okay, good afternoon everyone. Hope stopped. Okay, it started recording again, that's good. Yeah, I'm Dave Jenkins from Heriot-Watt University and I also lead the Energy Efficiency in Buildings theme within ETP. So to start off, hopefully most of you know who ETP are and what we do. But just as a reminder, we're an alliance of 13 Scottish higher education institutes engaged in various bits and pieces of energy related research across Scotland, with the intention to try and communicate this research to industry and make it more actionable and transferable to a place where it can actually have impact. So with energy being quite a broad theme, within that we have 12 sub-themes within ETP and it's energy efficiency in buildings that we're going to be focusing on today. Clearly there's a lot of interlinking between those 12 themes and the sort of cross-sectoral work that goes on. There's lots of ways of getting involved as either academics or as industry representatives. So we have an industry doctorate program that's live right now, which part funds PhD programs with industry, with an academic partner. There's also the Knowledge Exchange Network Feasibility Fund, which provides some funding for academic consultancy to be direct research towards an industry-based problem. And also just ETP more generally as a network. We obviously want people to join energy efficiency in buildings as a theme. We're in the process of developing a mailing list now around this theme, so keep an eye out. And if you don't feel you're in the loop of these of communications at the moment, then do let us know. We have Tom Bent and Laura Finley as the business development managers of the energy efficiency in buildings theme. We'll be happy to take any queries, and I've got some information at the end of the slides as well. But just to move on to the purpose of today, around this energy efficiency in buildings theme. So even as a sub-theme, it's still a pretty broad thematic area, lots of things going on, lots of different disciplines, lots of different sectors that are interested in this area. So we're trying to sort of pinpoint where the innovations are and innovation that can actually be actionable and demonstrated. So blue sky research is great, really valuable, but we're trying to identify a pathway between that research and something that actually has an impact on the ground. And that's why it's so important to have this industry link and engagement. But it's also important to understand what the baseline is, so to try and understand where we are essentially. So what do we currently do within this theme that's good, that's effective, and where are the gaps to the research? Where do we need to either elevate the research itself or try and communicate the research that's already going on into a place where it can have greater impact? So I've chosen 3 different areas that I think are particularly important, but on another day, it could be another 3 areas, quite frankly. But first of all, most of us will be familiar with energy performance certificates. They're pretty ubiquitous in terms of their kind of visibility within the built environment. EPCs are roughly 18 years old in terms of how we currently use them. They came from the European Union Energy Performance in Buildings Directive, so it's not just a UK thing. We see very similar processes across most of the original EU member states. In the case of the UK, the calculation methodology goes back quite some time, depending on where you define your year 0, but it could be argued that it goes back 26 years. So this isn't a new approach to how we calculate energy consumption, the standard assessment procedure, as we now call it. And of course, that's undergone many updates over those 26 years. But the kind of philosophy, the sort of starting idea of the kind of calculation we'd be using, is not new. It's a steady state approach, effective for what it was originally intended to do. But it's been around in different forms for quite some time. And it's important to remember this because it was originally designed to indicate ballpark energy efficiencies of properties, accompanied with some guidance for making them more energy efficient, where that guidance was fairly generic, but potentially useful and meaningful to a building owner. One of the issues we have now, and we see this in various research projects and also on the ground, is that we're changing how we want to use EPCs in policy. So we're potentially going away from guidance to actually mandatory action. So potentially using EPCs, or actually it's enshrined in policy now that we are going to be using EPCs for punitive and mandatory measures for enforcement of legislation. And that's a really different world to be stepping into with this type of model. And we need to ask ourselves, does that different end goal require a different mechanism? If we're trying to do something fundamentally different, is it right? Is it proper? Is it necessary to use essentially the existing system that was in place to do that? And some really nice projects across the UK, but also across Europe, because as I say, this is a Europe-wide issue. There's some nice Horizon program funded work at the moment looking at what metrics can you generate from an energy performance certificate if you wanted to put some new metrics on the actual certificate itself, but also what metrics should you be doing. Just because you can do it doesn't necessarily mean you should stick on that extra performance indicator just because you happen to be able to generate that number through the model that you're currently using. So that's one area that I think would be particularly interested in the coming years in this area. Another one, which I think we're going to hear a little bit about with our presenters later this afternoon, is around simulation at scale. So there's this very traditional assumption with building energy modeling, that when using dynamic simulation, so more detailed 3-dimensional building models, such as what we're going to hear from IES later, you can't dynamically simulate thousands of millions of buildings efficiently. It's the hardware and software limitations means that it's very difficult to do that at scale efficiently. So this is what leads us towards simpler forms of modeling when we're trying to assess the energy performance of many buildings at the same time. But if we look actually what's happened in the last decade around hardware and software developments and our own understanding of building energy performance, we should ask the question, does this assumption still hold? Why not simulate towns, cities, countries using effective forms of dynamic simulation, maybe with a sort of heuristic approach where you're looking for suitable shortcuts to draw in some of the kind of fundamental physics that these models understand, but also accounting for the fact that these things have to be used at a certain scale. That means they need to be efficient. And if we can do that, what extra information does that give us? Kind of referring back to this idea of generating new metrics to understand things around, might be overheating of buildings or demand flexibility issues around buildings. Does this give us a new level of insight if we're able to tap into this type of modeling? I've got an example there just on the left from one of my researchers, Peter McCallum, on the Reflex project, using GIS data quite efficiently to generate lots and lots of building models at the same time, which can then all be modeled dynamically in a reasonably appropriate and suitable timescale. So these things are possible, and it's just the question is, how do we actually transport that across to areas of policy and application where they can have again maximum impact? And then a final issue that I think that's of clear importance in research and is suitable for the likes of ETP because there's such a requirement to have good links to industry to actually get this to work, is the use of demonstrators and real energy data to enhance our understanding of energy in buildings. So we often, traditionally, we might have modeled to effectively replace empirical data. So it might be a baseline issue where we just don't have all the energy data at hand in a sort of measured way. So we have to use models to fill in the gaps. Or perhaps we're trying to model a future scenario where, by definition, we don't know what's going to happen yet. So there's always a role for modeling in that area. But in terms of the baseline, our sort of current understanding of energy use in this big data age, we can now use real energy data far more effectively to fill in the gaps of our knowledge, rather than just default go into a sort of purely theoretical model. And we're seeing more use of things like what might be called semi-empirical models. So they have a physical calculation engine, but they're informed by real energy data or kind of iteratively validated by real energy data. So they become far more reliable in terms of specifying a real life situation. And in that kind of environment, how can we access that data and make wider conclusions from that data when we have, for example, restrictions around GDPR, which are going to prevent some types of dissemination of that data. GDPR is there for a really good reason, but we see with smart energy data, it is possible to get quite personal information out of a high resolution energy demand profile. So we have to be really careful with how we use that and how we disseminate that. And so we have more measured energy data than ever before, but that poses its own challenges when we are trying to do this wider spread dissemination. And just a note on the left there, just to prove that these demonstrators do exist, there's the Energy Rev consortium that includes a number of demonstrator projects, including Reflex Orkney, which we're involved with at Heriot-Watt, and also a couple of projects in Oxford as well. And then there's other projects like Thames Valley Vision. So there's lots of real projects, really well measured, metered, monitored projects that we can start to tap into and understand that baseline. But there's that challenge of how we disseminate that to make more generalizable findings. So those are three themes that I think are particularly important. I think we're going to touch on those a little bit on the presentations today. If anybody has any questions on ETP, either about the energy efficiency in buildings theme generally or ETP itself, then do get in contact. I'm happy to take any queries, but I shall finish up there. Thank you.
Thank you so much, David. Yeah, really agree. Such an interesting point about the EPCs, particularly in the movement towards retrofit. So yeah, we'll thank you for that. I'd like to now invite Professor Laurie McElroy from University of Strathclyde, and she's going to speak to us about the role of building performance simulation in meeting these really challenging targets that we have. Thank you, Laurie.
Thank you, Sarah. Just have a go at sharing my screen here. Hopefully you can all see that. Thanks very much, and thanks for your kind introduction, Sarah, and your introduction, David, which includes a few things that I will touch on, but maybe not in much detail. I think my job today is really to set the scene by providing some broad perspective around current opportunities for simulation. I'm basing this on my experience and observations, and hopefully some of these ideas, as I say, will be picked up in more detail over the course of the seminar by other speakers in more detail. David touched on targets, and the Climate Change Act of 2019 commits Scotland to net zero emissions by 2045. And in addition, the government's draft heat and building strategy, which has just been out to consultation, commits us to developing a new framework that will help to deliver the Scottish Government's vision, which is that by 2045, Scotland's buildings will be warmer, greener and more energy efficient. Now, Scotland already has a strong track record of setting world-leading carbon reduction targets, but how do we know whether or not these targets are actually being achieved, or indeed whether they can be achieved? We're also a world leader in Scotland in the development, delivery and application of building performance simulation, and you'll hear more from IES on this later, but it's a field that we've been active in since the 1970s. And Scotland has been the instigator of several initiatives that have supported the construction industry in adopting a computational approach to design since then. Those early pioneers were among the founding members of the International Building Performance Simulation Association, which is the only international organisation dedicated to improving the built environment through research and application of simulation. And there is a Scottish chapter of this for anyone who's interested in finding out more. But IBIPSA now has a community of over 4,000 members in 40 countries worldwide, so we can learn from what's happening in other countries and what the priorities in other countries are. However, we're still in a position where theory and practice, as David touched on, can be miles apart. And although this is being tackled through a number of initiatives at a Scottish and UK level, the potential of simulation to help us to address some of these issues remains, I think, underexploited. The COVID-19 pandemic has brought health-related aspects of building performance sharply into focus, in part because while we all knew that there was more to carbon reduction than building tight, the reasons perhaps for ventilating right have become much clearer in the last year or so. And a lack of consideration as to how buildings actually work and how people use them in reality has often led to all sorts of issues, particularly in the case of renovating buildings that people have used or lived in a particular way for a long time. However, we have the skills, knowledge and technologies to avoid situations like the one shown in this slide arising, but we need to be smart about the tools and approaches we use and how we use them. The graph on the left-hand side of this slide shows the prediction of growth of a particular species of mould under specific temperature, humidity, and air movement conditions, a simulated image, and it matches exactly what was found in practice on the right. But was arrived at by working back from the problem to the model rather than using the model for prediction. And this, as David touched on, is a growing trend. And beyond buildings, as we begin to emerge from the current pandemic, it's already clear that we have an opportunity to rethink our cities, neighbourhoods, and the way we live. And indeed, a re-evaluation of what normal should look like will be necessary to both minimise the risk of recurrence and to make sure that we're ready for anything like this happening again. Simulation will play an important role in identifying solutions to the problems we're now facing by testing new ideas about how buildings and places work, both at microscopic and macroscopic levels. I'm not suggesting that simulation holds the answers or that these are new areas of research, but they've suddenly risen to the top of the political agenda, which again brings them sharply into focus. Sorry, my slide didn't move on there. But to make a useful contribution, we need to be confident about what simulation can and cannot do. We need to completely rethink how we use our internal and external environments, and we need to establish whether or not we have the right tools and skills to support this new normal. Moving away from the obvious, is there scope to explore technological aspects of health and well-being on an urban scale? And for example, the role of safe and pleasant outdoor spaces may be obvious, but should we really be reimagining our cities based on social distancing, which seems to be going to be with us for a lot longer than we originally anticipated? And what is the role of simulation in that? Will we need schools with more outdoor classrooms, for example? And do we also need to how do we apply new ideas to old places? It's all very well when we're starting from scratch. As a result of what's happened, people worldwide are suddenly much more aware of the need for healthy environments and buildings, and the importance of health and well-being seems to have overtaken many of the more technical aspects of measuring building and spatial performance. And while technology has a role to play, it can't address cultural, people-centred matters such as public engagement, inclusivity, understanding what makes a good place, and the impact of all of these things on people's lives. And in this respect, while big data can help us to explore trends, small data based on observation, for example, is just as valuable in other ways. Also, from a built environment perspective, the construction industry needs to work with governments and businesses globally to provide safe, healthy places for people to live and work in, and to be able to do this quicker, cheaper, and better than ever before. There are huge pressures in terms of balancing environmental concerns with the wider needs of everyone on the planet, and this will affect how we design and use our buildings and cities. We hear a lot about smart cities, and we'll probably hear more today, and the use of information and communication technologies to enhance the quality and performance of urban services such as energy, transportation and utilities in order to reduce resource consumption, wastage and overall costs. But there are as many definitions of smart cities as there are smart cities. And all of this presents huge opportunities for innovation in terms of rethinking how we protect fragile communities and what we have, how we reduce emissions, how we manage scarce resources, and how we future-proof our infrastructure to make all places resilient to man-made and natural stresses. Simulation can play an important role in helping us to get things right first time in terms of integrating new ideas, materials and technologies, repurposing old technologies and planning healthier, better connected environments, but also in considering why we in the past didn't build, for example, on floodplains and how we are now living with the consequences of that. The need to find answers to the questions that only simulation can begin to answer will continue to grow, whether at a system, building or urban scale. As other than building and hoping for the best, only simulation can predict performance in reality. However, it has to be used responsibly and appropriately in order to give good advice. And to this end, there is, I think as already has been alluded to, an emerging understanding of the benefits of combining modelling with traditional methods such as performance monitoring and testing of outcomes through occupant feedback in order to refine predictions so that they better match what is really going on and so that we can understand why that is the situation that we find ourselves in. In other words, combining big and small data sets. But there's also a need to look to the past as well as the future, taking advantage of historical pre-technology approaches to improving air quality in buildings and cities to make them safer and cleaner, examining the advantages and disadvantages of mechanical versus natural energy systems, especially in terms of looking at infection risk, and scrutinising traffic and people flows in cities and buildings in order to minimise risks and to evolve more integrated, inclusive and holistic approaches to design and delivery, focused on what matters to those who use these amenities every day. This will also provide us with new opportunities to collaborate more widely with the politicians and social scientists who now find themselves needing to answer questions that they've never been asked before. Obviously, there will be barriers to overcome, and things that are simple in theory are often thwarted by issues relating to accessing the information and data we need. And we've already heard about the problems of getting around or working with GDPR. We've also found in the past that there are many ideas that promise much, but which fail to deliver. But I take heart from the range and depth of activities going on worldwide in this field, from the use of simulation to support government policy development and decision making for regional and national governments, for example, around building stock management and new approaches to handling big data at a municipal scale, to the role of simulation in accelerating the integration of smart technologies into smart grids, including everything from the deployment of renewables and clean energy at city scale to the role of simulation in moving forward on e-mobility, new generation battery power stations, to digital transformation and digital twinning at a building or city scale. In addition to a heightened public awareness of the importance of designing for well-being, there's a growing demand from industry for access to tools to support a much more integrated built environment. And while industry might not quite be ready to take on all of this just yet, we are already seeing an upsurge in interest in and an increased focus on health in enclosed spaces, such as combining simulation of fluid and particle dispersal in a variety of environments, such as supermarkets, and the link between this and city planning for people movement around urban environments. We live in an era where people expect instant answers for minimal effort, and this presents new challenges, but I would argue that simulation and modelling code developers are moving faster than ever on protecting those needing answers by providing simplified interfaces for results analysis with lower risk of error through the automation of tasks in the background. Specialists can now also offer cloud-based simulation services built on whatever CAD or BIM model their clients can supply. This is a game changer, eliminating multiple barriers to tool use in one go. Now, when I started out in this field, some of the things we now take for, thank you. When I started out in this field, some of the things we now take for granted were not even on our radar. I used simulation without any visual interface, relying on numbers and commas and hoping for the best when I sent my model off to the mainframe computer, which was in another building. I worked in a forward-thinking design practice in an office that was remote from our software developers at Strathclyde University and used a modem coupler, a telephone linked up to a modem, and simple simulations took all night to run. A few years later, I was lucky enough to become involved in a project called Combine, which aimed to develop integrated building design systems through which energy services and other performance characteristics of a building could be analysed using standardised IT solutions on a single platform. The idea was to allow designs to evolve from one stage of the design process to the next without having to create new models. But at that time, the lack of a common programming language and the lack of computing power meant we could only go so far. However, recently I was involved in an EU project that is doing precisely that. And not only is it allowing tools to interact through a single platform, it also allows, in theory, any tool to plug into that platform. And the aim is to support building managers, owners and occupants to understand better how their buildings work and how to provide them with access to simulation through a platform without them having to develop models. So without understanding how the simulation works, they can interrogate the system and access results with the model running in the background. Occupants can flag issues locally and the information is conveyed to the energy manager via the platform. So nearly 30 years on, what we dreamed about has actually happened. Thank you very much.
Wow, fantastic. Thank you so much, Laurie. What a brilliant presentation. Takeaways for me from that are outdoor classrooms. My son just started nursery this morning, so I would love to see outdoor classrooms. And of course, we all want instant answers for minimal effort. Absolutely loved the kind of journey, the 30-year journey there. Fantastic. Thank you so much.
Shouldn't be admitting that.
Thank you. I'd like to now invite Rogério Guida from IES, and he's going to speak to us about decarbonising the built environment using digital twins. Thank you, Rogério.
Oh, thank you, Sada. Just let me share my screen.
Of course, yeah.
Okay. Can you see my presentation? Yeah. Can you see my screen? Oh, excellent. Okay, so first, a couple of words about IES. Maybe some of you know the company. I mean, IES has been working in building sustainability, building efficiency for the last 27 years. We estimate that we have made around 1 million buildings more efficient. So we're talking about large buildings and medium to large buildings. But a few years ago, we realized that one building at a time was just too slow. If we want to make an impact, if we want to decarbonize the built environment, we have to do more. And we found two main issues. One was dealing with the operation of the building, because you're probably all aware of the problem with the performance gap, the difference between the simulated energy consumption and the actual measured energy consumption. And plus, we realized that one building at the time was just not enough. So we had to scale. A community scale, that means at the neighborhood, the city, the country, eventually. Our CEO is dreams a lot at a continent level. So we've been focusing in the last few years in, let's say, developing our concept of digital twin. So let's just start from the definition. We embrace the typical definition of the digital twin is a digital representation of a physical asset. And we see three main pillars for the digital twin. The first is the data, of course, that we need. The second is the visualization. And what is more related to our, let's say, webinar today is the modeling. The modeling is very important because the modeling is about the behavior of the building. And we need to model the behavior. We need to properly describe the behavior in order to make predictions. Now, there are different ways to do modeling. Unfortunately, yes, there are some, let's say, people that use still spreadsheets to do building energy modeling, but considering, let's say, more serious approach, in the current days, we are talking about mainly about artificial intelligence and machine learning or physics-based modeling. That's what IES in a way is known for. But we cannot focus only on buildings. I think it's been mentioned before, buildings are part of the city, they're part of the fabric of the city. The buildings are part of the network of all the resources that are in the cities, like the water network, waste network, telecommunication, and so on. In order to actually make an impact, in order to decarbonize the city, that is actually the goal, we need better to understand the interaction and the interaction between all the different assets. Now, nowadays, it seems that everything can be solved with data. That's in part true, but the problem is that nowadays we are not lacking data. We have a lot of data. What is missing? Information. So to translate this data in some information, there can be action in some way. Even regarding the digital twin is not an outcome by itself. The digital twin is an enabler. It's an enabler that allows to do different kind of modeling, different and new, and let's say more effective way of analysis, but of course also allows to engage much easily with different stakeholders. Now, just a couple of the market for the digital twin is literally exploded. These are kind of relatively old numbers based on pre-COVID times. So now definitely is going in a way in the right directions. But I would like to focus on some key aspects of the digital twin for the built environment that are kind of peculiar compared to, for example, the digital twin of an equipment in a factory. Now, first of all, when we talk about buildings are occupied by humans. So that means that we've got all the uncertainties that are associated to it. And then in the end, we know that every building is a prototype. Even your house is different from the house from your neighbor. It's used in a different way. The buildings are filled with different legacy systems for lighting, for HVAC, and so on. And let's say artificial intelligence in the past few years has been doing quite a bit of progress in helping in dealing with these legacy systems. And with regard in particular to building phases, to physics-based simulation, unfortunately, historically has been used only at the science stage, but actually we believe that it needs to be integrated in the whole building life cycle. And then one aspect that I think is very important, when we talk about policy targets, we always say we reduce by 30% by 2040, 2050. So all our models, digital twin or simulation, they need to keep into account this multi-year approach. And one thing that I see looking in the industry, look what's happening around us, is that in a way, this is the time. There are so many technologies that I see that are converging. And this technology starts, of course, the building information model, but also the definition of ontologies. So we're starting to call the various assets in the same way across different industries. This is fundamental if actually we want to build a digital twin of something that is more complicated. Physics basic simulation, of course, has been improving, not in terms of the basic principle, but in terms of the capabilities. Now we can run simulation at scale. We can run thousands of physics simulation on the cloud. And of course, there's the explosion of the IoT sensor and machine learning. So all these elements, they need to, in a way, to work together to allow to create the digital twins that actually we can use to decarbonize the built environment. And let's say our digital twin tries to, we are not against machine learning. We don't say that machine learning is not the ideal approach. I think let's say the best way to create a digital twin is to combine a physics-based approach with data that is coming from the building, from all the sensors that are nowadays installed in every building, in order to create some predictions that are much more accurate. Machine learning can be used, for example, to fill the data gaps. I've worked in the industry for quite a while, and data is never clean when it comes from the building. It doesn't matter how careful you are. So that means that we can actually combine artificial intelligence, a building physics model to create, let's say, the best of both worlds. So a digital twin that actually is effective and can be used. You can see almost physics constraining what the prediction of the machine learning model can provide, usually in a very kind of short amount of time. But I wanted to give a couple of examples of projects we've been working on, because this is not just about theory. We are creating digital twin. The first example is a campus in Singapore, in a young technological university. They have a very ambitious goal. Of course, they want to become the greenest campus in the world, and they have actually a goal that they want to measure. So we started immediately building a digital twin of the campus, and this was at the beginning of the project, when the amount of information was very limited. Here you see the advantage of using a physics-based model, because just based on the energy bills and the physics-based model, we could almost create a higher resolution picture of the behavior of the various buildings, so start to make a hypothesis of how to improve the performance of the cooling towers, for example, of the district cooling. And the next stage now is when we had access to the data that was coming from the building management system, from the sensors. And here is when we started the process of calibration. What calibration means to fine-tune some of the parameters that were initially assumed during the physics-based, during the initial simulation, fine-tune them so that we can have a much, let's say, precise description of the behavior of the specific building that not only matches the total energy consumption, but will also match the temperature in each single space. And once again, it's very important. All this process has been automated. And that's key if we want to provide useful tools to the engineers, to the analysts that actually are working on this problem. And the project was successful. They managed to reduce their energy consumption, their cost, and so on. And the fact is that we were using physics-based simulation combined with the data that was coming from the site also gave confidence to the investors. So they thought the return of investment was, let's say, more reliable, because it had, let's say, better analysis behind it. But digital twin is not only about, let's say, complex. Yeah, it's not only about complex calculation for buildings. It's also about engaging the community. Just the visual aspect I was describing earlier. This is a project in Nottingham. It was a development where the architects wanted to share the performance of the development with the residents and with the general public. So the residents can actually look on a shared dashboard. What are the performance of their home in comparison with the average UK? What's the performance of the old development with the average UK? But this is also used as a tool to engage people. This is the actual digital twin deployed on a touch wall, and the various people use it to communicate measures, to communicate interventions on the building. And the last two things that I wanted to talk about is, I know this graph looks complicated, but buildings are part of the society. So we can also use the digital twin to do some analysis that are not specifically energy analysis, but also socio-economic analysis. And we can start to ask questions: what the impact on fuel poverty when we actually improve the performance of the building? What's the impact of air pollution when we will start to have more electric cars, and so on? And finally, I want to go back to the previous, to what I said before about the long-term dimension. All the policies have a multi-year let's say, horizon. So with a digital twin, we don't only need to describe the minute-by-minute behavior of the building, but also the year-by-year behavior of the building. So we will be able to make choices between, is it better to replacing now and install PV panels in 5 years' time, or the other way around? And so I just wanted to touch on this key concept. And if you have any questions, please feel free to ask. Thank you.
Thank you so much. That was great. I certainly think it's really important that we start to think about integrating digital twins into the build cycle. And obviously, yeah, the long-term plans, because that's where all the funding is going to look. It's going to be a 5 to 10 year plan. So thank you so much for that. Really, really interesting presentation.
I'd stop sharing my screen now.
Dr. Julio Bros-Williamson. He's speaking from Edinburgh Napier University, and he's going to speak to us about the role of building, modelling and digital twin analysis. Julio.
Thank you very much, Sarah. I'm just going to share my screen.
I've taken into account your start time as well, just so you know. Okay,
great. Thank you for that introduction, and also for the previous speakers who have provided a kind of starting and a good introduction to some of the slides I'll be presenting. Good afternoon, my name is Julio Bros-Williamson, and I'll be looking at the role of building modelling and the use of digital twin, actual use of it, and analysis looking towards lowering carbon emissions in dwellings, essentially. So just as a means of an outline, brief introduction, and also some of the points around digital twins and built environment and some of the benefits. And I've also got a case study, a live case study that I've been working on over the last 6 months, and that will progress over for the next couple of years. So hopefully I'll kind of exemplify some of the work that we're doing around digital twin there. So, I mean, digital twin interpretation of buildings has really moved quite swiftly, and in such a way that really requires a lot of more accessible and accurate data. And we know the power and how compliance models have been used over the last couple of years, and for many projects out there, especially new buildings, where we've got calculations that can be regarded as a good indicator of assumed performance. So this is kind of as predicted performance. But they do tend to kind of present that kind of unknown and a promise that kind of assumed performance will actually be the real performance, and that often is not the case, and very much can bring some problems there in terms of how that building is going to perform, and especially throughout its lifespan, which is not really what's happening. So there's concerns around performance gap, but there needs to be that analysis of the lifetime carbon of buildings, and certainly looking towards some of the targets of net zero and whole life performance. Now, digital twin has been used in other industries, particularly the automotive and aviation industries, where they're trying to, or have been for many years now, trying to perfect their designs, trying to use a lot of existing performance to inform models and to refine them to a better way. So that's something that I think the built environment is embracing. Now, within the built environment, digital twins provide this invaluable virtual asset that previous speakers have been alluding to, and that continued analysis of buildings and the operation of them, which is essential. We're not in a mode of just designing, building, and then letting it work on its own. There needs to be that analysis during the use of these buildings, and I think that building modelling it's got that capacity of giving that optimised approach, providing some scenarios of what if this happens, what if some changes can happen, and what the kind of impact of these changes can be, without really going down the risk of implementing them and then waiting to see what happens. There's that predictive analysis, but a more informed analysis with the digital twin. And I think that's where the optimization of the model, looking at future performance, is essential, whereas before it required a great deal of triangulation of data, multiple sources that some of them didn't align properly, and more assumptions were made with more data, which could be kind of less reliable at times. But luckily with the digital twin, that's kind of improved because there's that alignment of information and the technology around it. And there's that option of future scenario testing that can bring in maybe maintenance regimes or other approaches into the operation of a building. I really like this diagram here on the right hand side by Deloitte, where that kind of gives us an example of how we can create a physical asset, communicate a lot of its performance through the use of a digital version of it that can analyze it and gather a lot of information and refeed it back into the loop of the use of the building and maybe correct some of the faults that it might have picked up on the way. So a lot of the benefits really is to kind of be able to calibrate the actual as-built model to really look into performance scenarios, and that gives us an opportunity to interact much better with the users, with the technology that's been used, and to maybe look into maintenance and possibly retrofit options. That can later bring in savings in carbon emissions, energy, and also the cost of running these buildings. And when we've got a lot of problems coming in with the climate change and the impacts of them, there's also an opportunity there for modelling and to create different scenarios to mitigate the impacts of climate change and certainly to the comfort of the users. So trying to gather that real-time performance within this model and providing that clear and responsive approach is really key to the digital twin. So this brings me to the case study that I've been involved in, and it's a live project called the Edinburgh Homes Demonstration. And it comes from the need to provide new homes around the Edinburgh and southeast area, trying to deliver some of the requirements there for housing, and certainly trying to meet some of the net zero commitments by 2040, and before that, if possible, by the 2030s, and trying to obviously link in with the low carbon heating legislation that's coming in. But its primary aim is really to address some of these issues in terms of low carbon living, net zero compliant homes, and also trying to create solutions through innovative offsite solutions and methods of construction and efficient manufacturing of these, with objectives around meeting a lot of the local authorities' requirements, good understanding around the design and the procurement process, and also to bring in the testing and monitoring of designs back into the loop, back into the design part of future developments. And I mean, the Edinburgh Homes Demonstration is compiled with a series of other work streams. Edinburgh Napier is involved in the whole life performance analysis of a pilot study, and working with funding from the Scottish Government Low Heating Technology Fund and also Construction Scotland Innovation Centre. We're working very closely with Edinburgh City Council and others to really bring in this project management, the analysis of the demand of housing around the area, together with a design catalogue that can respond through procurement and also this whole life performance and being able to test it through a demonstration project. And luckily we're working with Offsite Solutions Scotland, with the offsite timber manufacturing teams, and Isabel Christie as the main architects in the City of Edinburgh Council. So really the case study and the work that we're doing is, first of all, looking at the techniques around the use of digital twin and building information modelling analysis of the prototypes and the pilot study designs. And it's based around digitising offsite components and floor plans as well, and also looking at the use of building performance and post-occupancy evaluation data that can be used back into the models to calibrate the performance of these and to learn from them essentially. and to use it as a tool that can be deployed into other developments. So this is a small kind of pilot study, but obviously there'll be other developments growing around the area. Within that, we're looking at digital components and standardizing some of the timber offsite construction methods so that the design can be met through the performance standards that have been set and can be deployed much faster, and the different contractors are familiar with the systems and can be constructed in a more efficient way. And there's ways in which we're doing that with the use of digital kind of components by changing the width, insulation types, the performance around it, and learning from it and really optimizing it as best as possible. So it can be different iterations of the same different components to bring that performance to life. But in terms of the calibration of the digital twin that we're doing, we're modeling a sample of some of these flats that are part of this pilot study, and we're trying to refine the models. And that's really through this continuous data input of the model that we will calibrate in real time with measurements, both in the envelope performance measurements that we'll be doing very early on, and also continued performance once they're occupied. So we'll be creating a baseline model through the design, and also looking to input manual calibration using, for example, air tightness tests and in situ values, and also with the use of automated real-time data through sensors that will be deployed in a sample of these. We'll be able to marry that in the digital model and optimize and start to look at ways in which the design can be improved and obviously deployed into other larger data sets. And we're hopeful that that will bring in savings in cost, carbon emissions, and energy. But really, we're trying to look at these assumptions that can be tested in real life with real life occurrences as well, and obviously bring in that data feedback. So in terms of the optimization and the reduced carbon emissions, the objective is really to reach net zero as best as possible, and to provide this model and this kind of methodology of building to other builders and to other construction systems and developments, so that there's a streamlined approach towards net zero, and having a confidence that it will meet net zero performance. And through that, there'll be a design code based on real-time learning that from the digital twin. And whenever the dwellings are kind of at a stage where they're kind of not meeting the standard, or they're derailing themselves from that design or from what that optimized option, there'll be an opportunity to correct that and to maybe look at ways in which there might be improved maintenance or an action for retrofit of certain aspects of the build. So it's very much looking to learn from the data for future developments, but also making sure that the development in question is actually performing in the future. It's and throughout its long time of use. So really, that challenge is to bring that design-based data from similar buildings, in this case, in this pilot study, to standardized some of the components, and to bring that and to operate the future developments through BIM and other digital twins that might be in use. So that's really what I want to talk about in terms of the digital twin and how we're applying it. So happy to answer any questions at the end of the whole sessions. But thank you very much.
Thank you, Julio. That was excellent. So glad you mentioned one of the projects we're working on together. It's like the Edinburgh Homes Demonstrator is just a really great example of where it's industry, academics, and the public sector working together. And as David mentioned at the start, it's that action-based approach. You know, it's research that's going to have real life, impact. So yeah, great. Thank you for that. I'd like to invite Donald McSqueen to talk next, and he's from Greenspace Live, and he's going to tell us all about Ecolab.
Hi, Sarah, thank you. I'll just share my screen.
I think you might have to stop sharing, Julio. Yes. Yep, can see you now, Donald.
Okay, are you seeing my screen now? Yes.
Not yet.
Not yet. There we go. That's it. Should be it.
That's you.
Yep. First of all, a quick introduction to Greenspace Live and who we are, where we came from. The company was originally set up within the University of the Highlands and Islands, probably about 15 years ago. About 10 years ago, it span out as a private company with some private finance. It's been surviving ever since. We're a pretty small company. There's only 3 of us at the moment. We have a couple of products that we've taken to market. One which we've sold globally is Gmodeler, which is a plugin for SketchUp. Allows you to produce a GBXML output files, which can be used in other energy tools. It's not a simulation tool itself as such, but it is a route to get in the building geometry into other tools, and it's used globally to quite a lot of sales in France and Switzerland using the SSI, I think it is, simulation tool. We can also generate an IDF file, which can be used in the Energy Plus simulation engine. And it will generate an NCT file, which will export the geometry that you develop in SketchUp to ISBEM for doing energy performance certificates. So that eliminates a lot of the tedious process of entering the building geometry in ISBEM, which is, there are other ways of doing it, other tools that will bypass that. But a lot of people still use ISBEM and enter all the data using spreadsheets and manually plugging in areas and measuring from drawings. It'll also import GBXML from other BIM tools, so you can then export them as either IDF to Energy Plus or NCT to ISBEM. We also have a cloud-based user interface for Energy Plus. Energy Plus is a dynamic simulation engine developed by NREL, who are part of the US government. It's open source, but not the easiest tool to use by a long shot. And even the kind of interface that we've developed for it, which includes a graphical representations of the node and branch connections and the systems within it, make it a lot easier to follow what's going on within the IDF file, which is basically a text editor. It's like a large program file. It's still very much a niche market, and we don't have very many users for that. But what I really want to talk to you today about is Ecolab. Ecolab is a joint venture between Chapman BDSP, who are a large building services consultancy based in London, but international. Curry and Brown, who are a large cost consultant, again based in London, but with an office in Glasgow and I think also Edinburgh. They provide a lot of costing information for our projects and have got a huge number of projects under their belt that we can delve into to get the kind of data that we need for background costings. Archetype are an architectural services consultancy. They specialize in passive house design, also based in London, but with an office in Edinburgh now. And ourselves, Greenspace Live, we are the software developer on the project and also provide some of the energy expertise, although most of that comes from Chapman BDSP. Ecolab stands for Energy Cost and Carbon Optimization, and we have modules for calculating the cost of buildings. Energy is done using the Energy Plus simulation engine, and we also look at all the embodied carbon. It's intended as an early stage tool to give the greatest impact, although most of our users seem to be using it on more developed projects. So we're having to change the way it works a little bit to work at later stages within the construction program. Early changes made will give very good value for money in your design if you try and make all your major decisions early on, because if you leave changes to later in the process, they become more costly, less effective. And if you leave design changes into the construction phase, then you're at the mercy of your contractor, and costs will rocket. This slide doesn't seem to have come through very well, but the Ecolab includes cost for both the capital and the life cycle costs. So it will look at the cost of replacement and refurbishment of items of the building, elements of the building during the life cycle. Also the life cycle carbon, both the embodied carbon during construction and the operational carbon and energy during the use and life cycle of the building. And that includes again, the replacement of elements of the building during its life cycle. Underpinning all that is a database of materials with all their properties. And that allows rapid analysis of the building by having all the properties of the various construction materials are applied through standard preset, predefined templates. You can very rapidly model a building and get results in the early stage without necessarily knowing all the details of what your building will actually look like. Material properties include the thermal properties of the material, which is used in the energy calculations, the embodied carbon to manufacture these materials and transport them to site, including biogenic carbon for things like timber, which actually have a beneficial carbon effect because they sequestrate carbon from the air and keep them in the building for the lifetime of the building. And also that database includes costing of all the materials. This provides a more efficient workflow by having all the main tools in one software package. It provides a holistic view of the whole building and the effect of changes and any design changes you make, and how they impact on all three of the cost, carbon, and energy parameters. So this saves time. You don't have to use multiple tools, and in the early stage of optioneering can be very valuable and saves a lot of redesign. So again, it does the costings and energy embodied carbon all in one, includes some certification elements. So a lot of the materials and wastage data that you put into the database of materials can also be used to populate some of the fields in, for example, BREEAM spreadsheets for doing BREEAM analysis. The materials library also allows you to upload supporting documentation like energy performance, environmental performance data to give an audit trail for your certification. And you can model many options all at the same time to see which ones will give you the most beneficial solution. The tool is designed for interoperability, so we can import geometry from various sources. Embedded in the tool is a building generator, which allows very rapid parametric models to be generated. But we can also import GBXML from SketchUp and IFC files from BIM, such as Autodesk Revit. It's a web-based interface, which means you can do all the heavy number crunching on the server. The user uses a basic PC, Mac, or tablet, just using a browser. A lot of options can be simulated in parallel, so it all happens very quickly without the infrastructure on your desktop to do it. We apply all the relevant standards. There are a number of carbon and costing standards in existence. Getting carbon data has been problematic, and a lot of manufacturers don't necessarily include carbon or report their embodied carbon in the same way, although there are standard forms. A lot of them miss out certain sections. Most of them miss out the end of life, what happens with disposal of these materials when the building is eventually decommissioned. Building services have been particularly sketchy, and earlier this year, SIBS published TM65, which is a calculation method for embodied carbon, which allows us to calculate the carbon within items of plant by breaking down the weights of different materials within that. We follow guidelines produced by RIBA and RICS. Also, the London plan is going to require life cycle carbon analysis for all the larger buildings built in London, and that will probably eventually percolate down to the building regulations and building standards. The cost model is based on breaking the building down into various elements. The structure is basically a parameterized engine at the moment, quite simple, but we're developing a more complex structural analysis engine. The facades are all taken from the geometry of the building, as are the roofs and floors, and the same elements are then used in the carbon calculation. I'll skip through the cost analysis, it's not so interesting. The energy modeling, as I said, is using Energy Plus, and that uses the building geometry and all the thermal properties of the materials to calculate the load. It's a fairly simple simulation. It's not a detailed simulation as you would carry out in something like IES. But it gives a very quick hit to give an approximation with limited data put in by the user. An awful lot of data is then defaulted by the system. The embodied carbon model is probably the most interesting part of this, because we look at the whole life cycle of the building, both in cost and energy, from design right through to the refurbishment or demolition of the building at the end of its life, including in use and construction. The middle graph here is probably hidden by the pictures on the side of your screen, but it shows how much of the carbon in the building is embodied and how much is operational, depending on the life of the building lifespan. A typical life cycle analysis is done on a 60-year building. At 60 years, we're looking at still more than half of the carbon associated with the building, with the carbon footprint of the building, is the embodied carbon during construction. That's partly the extract of raw materials, the transport to manufacturing locations, the transport of these products to the site, and then the construction of the building on site. And as we reduce, the operational carbon consists of both the energy use of the building and the replacement cycle of components within the building. So as we reduce our energy use more and head towards net zero energy, we still have a considerable amount of carbon tied up in the construction of our buildings. So it's important that we extend the lifespan as much as possible to make best use of that. The transport, there is a transport model built in which calculates transport carbon costs for materials being transported all around the world. And it's quite amazing how much stuff we move about the world and how much carbon that uses up. As I said, there's a materials library which includes all the properties of the materials that are required for the carbon and energy simulations and costings. In the early stage of the project, you can use fairly generic materials to get a very quick result. As the project develops, you can look at more detailed analysis using validated information for specific products. We also, as I said, have some certification elements to look at filling in some of the BREEAM information if you are looking at BREEAM information. And that's just a quick look at some of the outputs. That's me. Thank you very much.
Thank you. Wow, what a very technical presentation, Donald. Thank you so much. I think it makes really good points about the operational. We talk about the operational energy of the building, and actually it's the embodied carbon that's almost going to be the most important part over the next few years. So we're actually about to go through our own net zero, so I might be phoning you to use your product. Thank you so much. I'd like to invite our final speaker, Stuart Little from IRT Surveys. He's going to be telling us how we can exploit cloud computer to drive net zero decision making. Thank you, Stuart.
Thanks, Sarah. Welcome to my dining room, everyone. I'm just doing a little screen share. Is that working okay? Let it go full screen. So bits of this slideshow are a little bit dumbed down. I wasn't sure quite how technical you wanted this to be, Sarah, but having listened to the previous speakers, bits of it are definitely too dumb. So I'll fast forward a few slides. So just to begin with, to kick off, we're IRT Surveys, been doing thermal imaging of buildings for about 19 years. We started the company, my brother and I started the company back in January 2002 with Dave at the bottom. Dave wrote a computer game called Grand Theft Auto and subsequently went on to raise about £112 million and map every building in the world in 3D. We have a chap called Philip Selwood on our board, who's the ex-CEO of the Energy Saving Trust. We've got some venture capital and some housing specialists and a utility specialist on our advisory board as well. In that, I've rounded it up to 20 years, it's 19.5-year history. We've thermally surveyed 350,000 houses. We launched a platform called DREAM that automates retrofit decision-making on the cloud for housing associations. And that's what I'm going to focus on today, is just because that wasn't possible until cloud computing became a thing. We have done about just under 10,000 owner-occupier surveys. We have also surveyed about 700 medium to high-rise buildings, the majority of them being in Glasgow, flying drones down streets, looking for all sorts of different things, but essentially started as an energy survey. And some of our clients and partners are listed at the bottom there. So this is one of the dumb ones. I wasn't sure who was going to be on this call, so I put in a basic look, what is the cloud? Because we're, compared to the previous speakers, our customers are right at the point where rubber meets the road. There are clients that don't know what cloud computing is. There are people who don't understand human behavior. They don't know what a kilowatt is. They don't know what a joule is. They don't know how much they spend per kilowatt. So lots of our clients, we have to explain to them, look, don't fear the cloud. It's just like a server, but it's not in your room and you're not paying for it. They get a little bit apprehensive about the security of those systems. So I'll skip forward this slide because I think I'm teaching you to suck eggs with that one. Key benefits for us as a little company in Dundee is that we've got access to a plethora of computing power without having to invest in server farms. It's just a really nice, simple tool. So our whole raison d'etre, if you like, is to find houses that need to be fixed, help people engage in the net zero journey. We can help fund the solution and ultimately improve the asset. We developed the software I'm about to show you because it's a very, very complicated thing. You know, 80% of the buildings we'll be living and working in 2050 are already here, but what you do to them and how you fund it and who does it and how do you check that it's been done right is a real big problem. And someone earlier mentioned the performance gap. That's a very real thing. We get data sets sent to us from a variety of clients. We mash data, we augment it, we aggregate it, we map it, we model it, and it's never perfect, never. But you then factor in a bit of human behaviour, you factor in legislative changes, trying to mitigate risk from the valuation of the assets, from this funding landscape that changes all the time, and then factor in things like the clients don't have the resource that they once had. You know, especially the local authorities and housing associations, they've been paring back their human resource for a long time. So it's almost the perfect storm of, look, how do we fix this? We don't know what we're doing. So we developed this platform called DREAM. It takes the client's data, maps it, models it, shows up in a nice, simple interface. We've mapped things like fuel deprivation, the gas grid network, floodplain analysis. We've added in things like the funding that's available. This is a summary. This is nearly 400,000 houses for paying customers that are on this cloud-based platform. All those little dots represent the EPC and an actual house throughout the UK. I'm going to go through this really quickly as well, because I know you're all specialists. We can skin that data in any way you like. We can say, look, there's the maximum amount of funding that's available, it's £36 million. The average cost to run that house, where are those houses? We can get as granular as you like. You can say things like, look, show me the 3-bedroom semis that are E, F and G that are in Chester. How many of them are likely in fuel poverty and which ones need solar panels or light bulbs or a combination of both. We can also show you that as CO2. There's a heat map model where we've got basically the carbon output of each home fully modelled and mapped. And again, you can zoom in and in and in. This is on Google Earth and Google Streets. So it's quite simple to see, quite easy to use. We've analysed all the various funding mechanisms that are out there. So that's one thing no one really mentioned previously, is the key thing that's stopping an awful lot of innovation is available finances. And if you look at people like the Green Finance Institute, they've got a coalition of energy efficient buildings, which is full of guys like me and I guess some of the people on the call, trying to connect the money to the client, to the problem, and to various different solutions. That's pretty much what I just said there, sorry. We also, we've been fairly well known for doing thermal imaging. So we like to take the data in the top of the engine and then say, look, you've put 50,000 houses on it, let's go and thermal image 10% of them. Then we point out all the performance gap issues, like that house that's on your screen now was on data as being fully filled with cavity insulation. But a very quick one thermal image says that, look, the green bit is good, the red bit's bad. So it's a really simple, visually engaging way to say that cavity's half full. That's the optimist in me, half full. We also, back in 2006, wrote algorithms that can quantify energy loss. So we're the only guys in the world that can say, look, that's a before and after. The before's on the right, the after's on the left. It's two real semi-detached houses. But we physically worked out the size of every single pixel and then associated a U value to each pixel and reverse engineered how much oomph you have to put in to raise a pixel by 0.1 degrees. And then we can monetize that. And then we can associate the carbon to it and the kilowatts. This is my last slide. I've rocketed through this in turbo speed. the point of the cloud computing, I remember presenting in Aberdeen University once to a group of business students, and I told them the vision was to map and model cities and to create net zero roadmaps for each house and each commercial building. And an American girl put her hand up in the audience and said, she said, how do you expect to achieve this sort of thing from a country that's only ever given us haggis and bagpipes? So it was very refreshing to see those PowerPoints earlier from everyone to say that Scotland is right at the forefront of this. It was really, really exciting. I'm delighted to be part of it and share our little story. I hope that's got you back on time, Sarah. That was a 5-minute turbo speed.
Thank you so much. That was perfect.
Very welcome.
Stuart, really great presentation. I love the fact that you can quantify energy loss. That's just such a great visual on that. And I've got a few people that I could definitely get you to put in touch with that are speaking to me about the things that you're speaking about right now. So
that was all driven by one client in Aberdeen Council, Sarah, who said, we did 5,000 house surveys for them and said, look, what do you think? And they said, look, they're just pretty pictures. And then we went back a year later and said, okay, we've figured out how to monetize them. What do you think now? And they gave us about 20,000 to survey. And when we delivered them, they said, that's great, but you've very accurately described, we definitely have a headache.
Yeah. So
now we're on site doing a BASE funded social housing decarbonisation fund with Aberdeen Council. We've brought them £2.5 million of private equity. BASE have given us 2.2 million. And it's going, we're just about to start on site. And we've done loads and loads of work on that so far. 6 months of properly rolling up the sleeves, saying that house needs this one needs that, engaging the tenants, sending the tenants Amazon vouchers to engage them and let us do air pressure tests in the house and let us wander around in these COVID times. It's quite tricky.
I mean, it's a great example of like you say, where technology is having that real action-based impact out in the real world. So thank you so much. I think we've just about got 7 minutes left. So we do have time for questions. I'm not sure if anything has come up on the chat, so I'm just going to check. I think, Tom, you might have had some questions that were sent in. I don't know if you want to maybe share them, or if you can come off mute and let me know if we've got questions.
I haven't had any by email, so maybe encourage people to ask them on the chat. Let me just check on the chat right now. My chat's disappeared, actually.
Okay, let me just check.
There we go.
No, nothing on the chat. So have any of other speakers perhaps got a question from what anyone else was talking about? My brain is going blank.
Well, maybe just for any of the speakers, I thought it was great Stuart's closing point there about haggis and bagpipes, and you know, I think it was struck earlier by that Greenspace Live are busy selling products, you know, from the Highlands and Islands, you know, into France and Switzerland. So yeah, I mean, maybe ask any of the speakers, you know, where do they see Scotland in the context of you know, a potentially international world out in cyberspace? You know, what are our advantages and disadvantages?
I mean, I'll just add to that. Genuinely, in building simulation, I mean, those of us working in that area know that central Scotland in particular is a bit of a hub of energy modelling. So, and that's not just what Scotland thinks. If you go into international conferences, Scotland's always really well represented in the areas of building simulation and building modelling. So, you know, this, you know, we would say this, wouldn't we? But it is something that is generally recognised, and I think we can make more of that. And it's what's nice as well is it's not just academic, it's not just industry. It's both. It's the academic research and a number of companies in this field. We've seen some of them today. And so yeah, we need to try and make more of that, actually.
Yeah. Laurie, I think you've got your hand raised.
Yeah, I'll put my hand back down so I don't forget. Yeah, I mean, I'm just echoing that. I mean, I know I took you through a 30-year romp, but But actually, I don't think any other country, a lot of countries talk a good game about moving simulation from academia and research into practice. But one of the things that we've done in Scotland that nobody else does is that we don't just take black box simulators and put numbers into them and believe the numbers that we get out. We want to get in deeper, and maybe that's just because of, you know, Scotland is really strong in engineering, and it's really strong in this sort of questioning field, whether it's building design or anything else. And so we've always innovated in this area, and it is a pity that Scottish and UK government ploughed a lot of money into this in the 1990s, even up to the 2000s, and then it all kind of dried up, and that's a great pity, because as I say, we have a lot of really great skills. I mean, we've got companies like Arbenco working out of the TIC Centre at Strathclyde, who are actually an American-based company who recognise how good Scotland is at this stuff, and they're exporting what they do back to America. So quite interesting to hear that somebody thinks all we've ever given the world is haggis and bagpipes, when we're all when we're all looking at screens and using telephone type systems to communicate today. But yeah, that wasn't really meant to be a nationalist plug. But yeah, I think that it's an area where the money dried up a bit at that point in time, because the investment needed to be so high. But if you even take it to the point of how we you know, I mean, I think that Stuart mentioned the guy from Grand Theft Auto. You know, how we actually improve the visualization of these that we have for these tools would be a really interesting area to get into. Money seems to be available to go into the visuals side of graphic interfaces and so on for games, but maybe we should be looking at more at how we can turn our computer simulation into more of a kind of, you know, take a more game-based approach. I don't know.
Yeah.
But it seems to be very hard to get money to do that kind of hardware and interface, whereas it's not so difficult to get money to do something that's very visual and game orientated.
Yes.
And there have been kind of forays into that in the past, you know, sort of creating environmental games for kids and things like that.
That's
We tend to want to kill the planet rather than save it.
Our experience of raising venture capital, it's not been too hard in the UK to raise venture capital as long as you ask for small amounts of money. But we've been across the pond. Scottish Enterprise took us to Silicon Valley, and we must have met a dozen VCs who all loved what we had, but they all said, we had about three big VCs say, look, we love what you're doing, but go away, build more traction in Europe and come back when you need 20 to 30 million. Oh. And what they're saying is, we want 10 times that back. So if we put in 20, we want 200 out. So within 3 to 5 years, build a company worth 400 million, because we want half the company for 20 million. And that's where the disconnect with Scottish companies comes, because British Airways isn't worth 400 million. You know, it becomes a real psychological barrier. But
I've heard that. Yeah, I've heard that before, that Scottish companies quite often are not ready to make that leap. They'll sell the company rather than make that leap, if you know what I mean. Yeah. They don't want to internationalize to that scale because it's too big, and I don't know why that is. But I've also heard it from looking at actually how you deliver what you're talking about. You know, it's not just the analysis of it, it's how we actually put that insulation or that energy system on the ground. It seems to be that we're always asking, according to some people I've spoken to in Scottish Enterprise, we ask for too little money for too small scale, and what people want to invest in is massive, and we don't have that capacity. Maybe we don't have that capacity, but maybe it's time we built it. It's like, you know, people go on now about the fact that we sold all our wind turbine expertise to the Danes and the Dutch, and now we're buying it back. You know, what is it about us that we only want to go so big? And that's maybe a question that Construction Scotland Innovation should be helping us to answer. I don't know.
Well, I do know that there is funding coming around the retrofit. A number of the city deals are looking at that, and it's 5 to 10 year programs, and it's big money. So hopefully, maybe this will be the start of some real action. Stephen Mark Williams has raised his hand.
Hi.
Hi.
Apologies for my my background.
No, you're all right.
Unfortunately, this is a problem which the UK and Scottish governments have been trying to solve for the last goodness knows how long. The fact is we have never been good at scale up. And I don't know what the reason is, whether we are risk averse or we're simply not a big enough country, but we don't do it. The ITIs were set up to do that kind of thing. The catapults were set up to do that kind of thing. All kinds of organizations have been set up to do that kind of thing, but we simply don't do it. And I don't know what the answer is. And I don't think Construction Innovation Centre is going to solve that problem.
I wish we could.
Yeah, I know.
But maybe we should be asking the question more, as you say, Stephen Mark, sorry.
Yeah, absolutely.
I mean,
okay.
maybe we like to do the research, and we don't like to, we like to go do the research, push it out, and go back and do more research. I don't know.
Yeah, we need to dream big, as they say. Well, listen, thank you so much. That's us come to the end. If anyone does have any other questions or comments, please share. We're really interested in your opinions. We're going to send out a short survey. And it's just left to me to say thank you so much to everyone for your presentations and your time today. Really appreciate it. And I'm sure we'll have another one of these sessions. And thanks again. Thanks for being here.
Thanks a lot, Sarah.
Thank you.
Thank you. Thanks for hosting.